Hello, good evening, sir. My name is Shivam and I have to present my topic on transmission electron microscopy and scanning transmission electron microscopy. So let us start with the content which has been included in the PPT. First, we have to go to the introductory portion. Then we have compared the different types of resolution with different types of microscopy. Then we jump to the instrumentation portion. Then we have to think about the working principle and the working mode of the transmission electron microscopy. Then we go to the imaging portion and discuss about the contrast. Then after different types of aberration and how they have been generated and how they has been removed. And in end of time we have a limitation of times. And the next section of the PPT we have discussed about the STEM and difference between TAM and STEM and which types of different detectors are being used in the STEM. And there's a video on STEM and the video on TAM. Animated videos also presented in this. And in end we have advantage and disadvantage on the TAM. So let us start the introduction portion, which is the first question we have already that, which is what is microscopy? So basically, microscopy is approach to see things which are not seen by our naked eyes. Yeah, there's a little bit history about microscopy that the field of microscopy dates back at least 17th century ago. The microscopy is further classified into parts. The first one is the optical microscopy and second one is the electron microscopy. Now we have to go through the differences and similarities in between these two microscopy. So first we have to see similarities. The first one similarity is between these two microscopies that both involves the phenomena of diffraction and refraction and transmission. And second one is that both types of microscopy uses same instrumental parts like illumination lenses and viewing apparatus. Coming to the portion of differences, the optical microscopy and electron microscopy. Within optical microscopy, we use the visible light as a source, and there is no need of vacuum in the optical microscopy, and the images we get from the optical microscopy has the low resolution. On the other hand, in electron microscopy, we use electron as a source, and there is a need of high vacuum, and the image we get from the electron microscopy has the high resolution. So, a question is arising here that is there is a relation between the source and resolution? See, as we have taken a visible light as a source and we get a low resolution, and here we use as an electron as a source and we get a high resolution. So, yeah, there is a relation between source and resolution. First, we have to think about the energy of source decided the wavelength. Yeah, this is obviously, and the wavelength is largely determine the resolution. So this is as a calculation between these. We have which type of source we have to take and from where we get this type of resolution. Now we have coming to the next session that how many types of electron microscopy and what are their relative comparison between their resolution. So there are several types of microscopy depend on the which types of electrons they have collected. First one is that surface electron microscopy, transmission electron microscopy, and further there is a electron energy loss microscopy and AES, STEM, and cathodoluminescence. So these are different types of microscopy within electron microscopy. Now coming to the next session, that what is resolution? So basically, resolution is the up to which minimum distance we visualize the two closely spaced objects. This is what we call a resolution. Now, this is a picture that has been taken from the AR West book. Here we see the relative resolution between the our from naked eyes to the STEM. So we have seen that our naked eye is the least resolution, followed by the optical microscopy and SAM and after TAM and after STEM. So we see here that optical microscopy has a little bit less resolution than the trans electron microscopy. Now, further, our topic is that transmission electron microscopy. So we have go through the instrumentation portion first one. So this is the systematic diagram of the instrumentation, which has been drawn in such a way that there's a various types of parts in instrumentation. So basically, we can classify these instrumentation portion in majorly four types. The first one is the electron source. Second one contain electromagnetic lenses. In further section of PPT, we discuss about various types of electromagnetic lenses. And second one is the specimen stage. And in last one, we have discussed about the different types of detectors. So we have discussed all component by one. So first one we have to discuss about the electron source. Electron source basically also called as electron guns. Basically, we have a cathode from which we have to eject the electrons. So based on these electrons are further accelerated by a high voltage to form a high energy beams. So based on that, how we eject the electron from the cathode, the electron sources are further divided into two parts. The first part is thermoionic emission gun, and second one the field emission gun. In thermodynamic emission gun, based on the different types of cathode, we have further classification. See, first one is if we take a tungsten filament act as a cathode, and second one is the lanthanum hexagonide can also act as a cathode. And in on the other hand, in field emission gun we have a cold field emission and a hot field emission. Basically, what is going to be here that in thermodynamic emission gun we give a temperature to the cathode to release the electrons, and in field emission gun we use a electric field to emit the electrons from it. So this is the classification of these two electron sources. Now, is there is a impact of increasing accelerating voltage? So there are two impact has been seen. That first one is that if we increase the accelerating voltage, then we increase the resolution. And second one is that if we increase accelerating voltage, then it may cause specimen damage. Now coming to the electromagnetic lenses, here we have seen that there are two questions. That is there is a same types of electromagnetic lens or glasses lens basically is they are similar to the glass lenses or normal lenses. And second one is that why especially they are required. So answer of first question is that they are not the normal lenses just like we have used in the optical microscopy. And why especially they are required, this is explained in the further section. So electromagnetic lenses are analogous to the glass lens used in the light microscopy to focus light. So basically here we can say that which work has been done by glass yeah, normal lenses in optical microscopy. Similar work is done by electromagnetic lens in the electron microscopy. So why especially they are required is here electrons are the negatively charged, so they are manipulated using the magnetic fields. So to control or manipulate the direction of the electron beam, we have to use the electromagnetic lenses. Further, it has been used to focus and shape the electron beams. Without these lenses, level of magnification and resolution is not to be achieved. Now coming to the next portion that how actually electromagnetic lens look like. See, this is the systematic diagram of the electromagnetic lens having a coil and a north and south pole. And he said that a parallel beams of electrons has to come, and after that we converge into a particular focus. So a magnetic field is also concentrated between the north and south pole is to focus electron beams. Now, in actual our transmission electron microscopy system, our transmission, how our electromagnetic lens look like in real world. So this is the picture of the electromagnetic lens, which is actually real. So there are many components has been indicated here. So first one is that yeah, this is a cylindrical shape contain the copper coil. Basically, this copper coil is responsible for the generation of the magnetic field, which has to control the direction and the shape of the electron beams. Second one is these two holes are the related to the cooling water system. So basically, when we give to the current and the generation of the magnetic field, then there is a consequence that the electromagnetic lens get heated. So to maintain the temperature of the electromagnetic lens, we have the cooling water system. Here one it is one from one water is inlet and from second hole the water is outlet. And last this is electric connection provide current to the coil. Now there are various types of electromagnetic lenses and there are some specific properties of them. So we have discussed these one by one. So first one is the condenser lens, which has been used to focus the electron beam on the specimen. Second, then show the size and shape of electron beam before it interact with the sample. So basically condenser lens is placed before this specimen. Now second one is the objective lens. It is used to focus the electron beam after it passes through the specimen. Second, that it determines the resolution and magnification of the final image. Basically, it is just below the specimen. So condenser lens is on the top portion of the specimen, and the objective lens is placed below the specimen. Third one is the intermediate lens. This lens is not necessary that it may be present in all time setup, and it has role to control aberration. So what is aberration? This has been discussed in the next portion of the PPT, and there are many types of aberration and how they are removed. They are discussed further. And fourth one is the projector lens. This lens has to magnify the image to form the objective lens and to project that magnifies image on the screen. Basically, it is also names also concluded that this is a projector lens, basically to project magnified image on the screen. Now there's a how we have prepared the specimen. So there's a requirement of the good specimen. What is the requirement of that? There's only one condition that it should be thinner. But up to which range it should be thinner? That thickness is up to sample up to 100 nanometer. So this is going to be some observation regarding the specimen preparation is that specimen preparation is a crucial step in time. The method we choose for sample preparation is depend on the nature of the sample. So if we have different types of sample, then we have different types of method to prepare a thinner sample as much as possible. So overall, we have to conclude it in two main types of steps. The first one is the pre-thinning. This step is done for all types of samples. After this process, we get up to 1 millimeter thickness, and the method which we done majority we done in this pre-thinning method is mechanical stress, and second one is the grinding method or also be to use. Second step is the final thinning. After this final thinning, we get a thickness of 100 nanometer has been achieved, and the various numbers of methods are has been used in during this depend on the which types of our specimen has to be. For example, if we have a metal specimen, then we use electrolytic thinning. If we have ceramic material, then we use to ironing milling, and if we have a polymer types of specimen, then we do a ultra microtone cutting. These are further classified in many ways, but at that point, these are three types of final thinning process based on the which types of we have a specimen. Now coming to the this is the one of the animated video on TAM. The link has been given in this, and if here we can see that these are the orange lenses and these are the green color is basically the beam of the electron which originated from the electron sources, and these orange portion is basically is the electromagnetic lenses. Now this is the picture of the TAM facility in our IIT, which is placed as adjacent to CCD. Yeah, here we can see this is that our TAM facility is much larger in the size. So this could be the one of the limitation of the TAM we have discussed in the later section of the presentation. Now coming to the portion working principle. Yeah, here we can see that if electron beam has to interact with the specimen, then there are a various number of interaction has been possible, and on based on these types of interaction, there are different types of electron microscopy has been defined. For example, this is yields, and if we collect the only inelastic scattering electrons, then this going to termed as yields, and this is the coherent elastic scattering SAD and CBD. This is the portion which has to be discussed in the transmission electron microscopy. Further, all has over electron microscopy and the cathodoluminescence. So there are some observations regarding the interaction with incident electron beam and the specimen. So first one is that electron beam shows a number of interaction with the specimen. Second one is that accelerated electron can pass through sample without interaction, undergo elastic scattering, and can be inelastic scattering. Yeah, there is both types of possibility here. Third one, there the transmission of scattered electron is inversely proportional to the specimen thickness. Okay, and fourth one is that incident electron that are scattered by atom in specimen electric fashion follow Bragg's law. This has going to be discussing further that we have two modes of transmission electron microscopy. One is image mode and second one is diffraction mode. So in diffraction mode, we have to discuss about the Bragg's law, that if we follow the Bragg's condition, then we get a diffraction pattern of the specimen. And this portion that the transmission of unscattered electron is inversely proportional to the specimen thickness. So we have basically required a thinner sample as much as possible, because we have to make our specimen as electronically transparent. So more number of electron get transmitted through it, and we get more number of information regarding the specimen. Okay, now coming to the portion of working mode. Yeah, there is a two working mode of the time. First one is the diffraction mode and second one is the image mode. In diffraction mode, we have to collect the reciprocal portion. So here we have discussed that for diffraction mode, intermediate lens is focused on the back focal plane of the objective lens where the diffraction pattern formed. And for the image mode, intermediate lens is focused on the image plane of the objective lens. So basically, time can work in both mode, diffraction mode and image mode. To switch between these modes, the major role played by the intermediate lens. Basically, the position of intermediate lens decide that time works in which mode, either is diffraction mode or either is in image mode. Now, there are another types of variation has been possible in the time, which is electred area diffraction and convergent beam electron diffraction. So these both types of diffraction has some specific there is speciality and has been used to different works. So coming to the portion of selected area diffraction. In this, we have choose a specific region of the specimen to be selected for diffraction analysis. Second one is to provide information about the crystal structure, lattice spacing, orientation, and symmetry regarding the our specimen. In the next portion, CBED, a convergent beam is used instead of parallel beams. Second, it gives detailed information about the local crystal structure and including stain defect. As it has a convergent beam electron diffraction, so it focus only a specific portion of the specimen through which we get about local crystal structure information. Now, as we have discussed earlier, that TAM can work in both mode. First one is diffraction mode and second one is image mode. So another technique which is X-ray diffraction is also gives data in the diffraction pattern in the form of diffraction patterns. So for a specific sample, we get diffraction pattern in two ways. First one is X-ray diffraction and the second one is SAD in time. So between these two diffraction pattern, we have to compare several data which has been followed. The first one is scattering nature. So in X-ray diffraction, scattering nature, the scattered by electrons, cell electrons. Basically, the scattering is happen by cell electrons. In time, the scattering by atom nucleus. On behalf of path lengths, X-ray works on the property of phenomena of the reflection, while transmission electromagnetic based on the work of the transmission. In comparison to diffraction angle, in X-ray diffraction angle, there is a 0 to 180-degree diffraction, and in time there is a 0 to 2 degree of diffraction. This has been correlated like in time we get moreover a parallel beam of electrons. So there is no much deviation has been observed. So that's why we get a minimum diffraction angle, while in the extra diffraction angle we get within a range of 0 to 180-degree diffraction angle. Now coming to the imaging mode. So let first we have discussed about the contrast. So what is the contrast? This is first we have to know before we going to different types of contrast. So basically contrast is the differences in the intensity of two closely spaced points. And second one is that the quality of image is basically decided by the contrast. So there are many types of method through where we generate the contrast in the image in time. So basically first one is the mass density constant, second one is the diffraction constant, and third one is the phase contrast. So we have discussed one by one these all types of contrast. First one is mass density contrast. So in density contrast, amount of scattering at any point on a specimen depends on the mass and density product at that point. And second one is that contrast in amorphous material arises from mass density contrast. So basically we have seen here that in mass density contrast, the difference in intensity from the a particular specimen has been generated from the decided by the product of mass and density at that particular point of the specimen. And this types of contrast has been used in the amorphous material. Now coming to the next type of contrast, this is diffraction contrast. In this, electrons are deflected when Bragg's condition are fulfilled. Obviously, we get a diffraction pattern when Bragg's condition are fulfilled. It is useful to determine the lattice defect in crystal material. It is very sensitive to the specimen tilting because we get a diffraction pattern when we have a set of imaginary planes called as mirror indices. So if we tilt, then these planes also get be tilted in the specimen and we disturb our diffraction pattern. So in further section we have also a picture which is related to specimen tilting and impact of tilting on the image. Now coming to the third portion, which is a phase contrast. In this, several beams are admitted on the sample, and the interaction of the scattered beams with the unscattered beams give a high resolution image useful to determine the crystal structure. Basically, this is phase contrast has been used into the high resolution electron microscopy. Now, this is our image we have got from the transmission electron microscopy. Yeah, there is a two region. One is bright region, and second one is a dark region. In bright region there's a less dense region deflected, so basically from this portion electron deflect less numbers, so we get here bright region. In dark region there's a more dense region and the electrons deflect more, so that's why it's a particular region in the sample we get the dark images. Now coming to the image different types of imaging mode. So there are some bright field and dark field, and there's a high resolution electron microscopy. So in bright field, we have collect the sample which come from the direct beam, and in dark field imaging, we collect the electrons which has been got deflected. So initially, it had been concluded that either we have to move objective aperture from to get these types of different images. This question has to be raised that whether we have to move objective aperture to get bright field image and to get dark field image. So this answer is no. Basically, we have to move the our electron beam source, and the objective aperture is still at their position, and we from that there we get bright field and dark field images. Both type of images give different types of information regarding a specimen. Now this is the imaging pattern we have got from the TAM. So basically, yeah, this is the bright field image of a particular sample, and this is the dark field image of a that same sample. So there is a concept between dark field and bright field is that in if we discuss with relative to the optical microscopy, then where we have a if we have a bright field image, then corresponding to it we have only one dark field image. Whereas in electron microscopy, corresponding to one bright field image, we get a number of dark field images. So in optical microscopy, we can say there is a one-to-one relation between bright field and dark field images, which is not follow in the electron microscopy. Here we get a number of dark field images regarding with a particular types of bright field images. And coming to this picture, this has to be discussed via the tilting of a specimen, impact of when we tilt the specimen and impact of that image. So in first image there is a portion 1, 2, 3 mentioned. The one portion is dark and these are the brighted. So if we tilt the specimen, then we get different types of images from the same portion. So we have seen that in first pictures portion 2 and 3 are going to be bright, but when we have to tilt our specimen, then the portion 2 and 3 going to be dark and the portion 1 going to be bright. And this is the comparison of dark and bright field images of LOA. This is the same sample. This is a bright field image of same sample at that time, and this is the dark field image of same sample, which looks like to be different. Now coming to the portion of aberration, that what are the aberration, and basically first question is that what is aberration? So aberration is basically a deviation from the ideal behavior of the electron beam as it passes through the sample and the lenses of microscope. So this is basically the definition of the aberration. Now, what is the impact of aberration? So it results in distortion of images. So coming to the next question, that there are three type of aberration. This is spherical aberration, chromatic aberration, and astigmatism. Now we have to discuss these aberration one by one, that how they are being generated, what is their impact on the images, and how they have been removed. So coming to the first portion, that spherical aberration. In spherical aberration, we have seen that that why it has been generated. So it has been generated when electrons are focused differently. This has been seen from that. This is a picture from the optical microscopy, that if we have normal glass lens, then our normal glass lens focus different, has multiple focus. So it has been made by applying another type of lens to get only one focus. So what it leads, if we have a spherical aberration, then it leads the blurring and the resolution in the image. So, and coming to the third portion, that how it will be removed, that it should be minimized by aberration corrector, which apply electromagnetic field to control electron beams. Now coming to the next portion, this is chromatic aberration. So basically, chromatic aberration arises due to the lack of monochromatic behavior in the electron beams, and it also arises when electron interact with the specimen and loses energy. And it should be corrected by using monochromator, using select a particular wavelength. So basically, we have think that our electron gun provides a monochromatic electron beams, but in actual, if it is not providing the monochromatic beam, then this types of aberration has to be generated. This is called chromatic aberration. Now coming to the third portion, this is astigmatism. This is a picture related to the astigmatism, which has been seen that maybe some vertical lines may be blurred, and there sometimes there horizontal lines more be blurred. So why it has been arises, that arises when the electromagnetic field around the optic axis is not uniform. It distorts the image in one direction, and it has been corrected by adjusting the electromagnetic field in the lens. So basically, astigmatism has only a relation between within the electric field around the optic axis. Now there is a limitation on time. So first one is that we have already discussed that there are time are very large and expensive. Their sample preparation is also a tedious step. Operation and analysis require special training. There is a vacuum chamber also needed within the TAM microscope, and further one TAM requires special housing and maintenance. Images are black and white, so there is no little bit less interesting. And in last, electron microscope are sensitive to vibration and electromagnetic fields, and must be household in the area that isolate them from the possible exposure. Okay. Now coming to the next portion of the our slide, that is STEM, scanning transmission electron microscopy. So there's one we have discussed about some basic characteristics of STEM. First one is that STEM is advanced imaging technique, visualize the structure at atomic level. So we have earlier seen in the resolution comparison that STEM is the highest resolution technique. Second one is that provide high resolution images along with the spectroscopic data, collect various signal in parallel bright field, annular dark field, and high angle annular dark field. And in last one, commonly it work commonly paired with the EDS and ILS also. So question is that if we have a TAM with a good type, roughly a good type of resolution, then why we need a STEM? So basically, we design the STEM to separate the probe formation optics and the detector optics. Second one is to develop the ability to collect multiple signal at a time. As in further section we discussed that in STEM we have many types of detector. Basically, these are different types of detector: bright field detectors, ADF detectors, and head-up detectors. So we discuss this later in the session. Second one is that which types of electron guns are used and why it is preferred in the STEM. So in basically STEM we use cold field emission gun is to be used, and why it has been used because of its superior coherence electrons. Basically, it provide a good type of electron beams, which is a fine probe optics. So this is the systematic diagram of the STEM. This looks like almost same as the TAM, but the difference is that of scan coils. These scan coils help us to make a formation of fine probe optics. Now coming to the point that how a STEM is different from the TEM. So there are many types of points points where we get difference between these two. So first one is that beam formation optics, which represent different convergence angle. So from figure we have also seen that in TEM mode, the convergence angle basically alpha, which I'm telling is equal to 0, and for STEM the large value convergence angle is to be needed. Now coming to the next session, that a magnification process. Basically, in time, the magnification process is basically decided by the properties of the electromagnetic lenses. But in STEM, the magnification is controlled by the scanned area. For example, if we have a scanned area of 1 millimeter by 1 millimeter, and we have to present it on our computer screen of at a region of 100 millimeter by 100 millimeter area, so we can say that we have a 100 times magnification. So basically, magnification process in the STEM, sorry, is not decided by the position of the electromagnetic lenses or work by the electromagnetic lenses. It only and only depends on the factor of the scanned area. In scanning, it's scanning small area also increasing magnification, and second one is increasing pixel density, increases resolution. Now coming to the third portion, which is the main difference between STEM and TEM is that the main difference is that beam CBD pattern may contain phase different contrast. This is because no parallel beams may follow Bragg's condition. Basically, it has been stated that in time we have got parallel beams, so condition to fulfill Bragg's law is to be low. While on the other hand, in S time we have a convergence angle, so here are more chances to be following condition of the Bragg's law. So there are many types of detectors that has been used in the STEM. So what is the role of detector? Basically, play same role as objective aperture do in the TEM. So first one is the bright field detector. So in bright field detector, basically typically angle of bright field detector is half of the convergence angle. Second one is the annular dark field detector. This is a ring shaped detector that surround the bright field detector, so that large portion of bright diffracted electrons has been collected. And third one is the high angle annular diffract dark field detector. So this is similar to ADF imaging, but collect electron that is scattered at high angle. This head-up detector has further discussed in the next slide. So there, from this figure, we have to see that this is in central this is a bright field detector, then in ring manner ADF detector, and there is a head-up detector. So angle also increases between these two. For example, this has a minimum collecting angle, and this is more, and further this is head of a more collecting angle. So coming to the head of detector, what is the specialty of this high angle annular dark field detector? Said that majority of that electrons it collects, basically majority of that electrons which is scattered incoherently. So where these such types of electrons are generated, that these electrons originated from the interaction of electron and the nucleus. So when there is a parameter comes according to nucleus, so contrast depends on the atomic number also. So head of imaging is also termed as jet contrast. Basically, because it collects the electron which have originated from the interaction of the electrons and the nucleus. Now it has a drawback also, which has been that contrast depend on the square of the atomic number. So in general language, so in a sample, if we have metal oxide, then only metal cation is visible. So we can that if we have a sample of metal oxide, so due to metal has high atomic number and oxygen has a low atomic number, and the contrast is depend on the Z square. So in our image, we get more about data about the metal and not about the oxygen portion. So this is the drawback, that it morally depend on the intensity, contrast depend on the square of the atomic number. So this is a animated video on STEM. So now coming to the portion of the advantage and disadvantage regarding the STEM. So advantage of STEM is that it gives atomic level resolution, simultaneous imaging and analysis, because we have a multiple detector system in STEM. Z contrast imaging, also. There is a versatility in situ experiment, and there is a high sensitive. Only regarding the disadvantage portion, as time as instrument complexity, there is a chances of sample damage. The sample requirement is also a challenging task in TAM and STEM both. Is resolution limit, electron beam damage, and there's a high data acquisition time. So they are the references which have been from where we have collected the data, basically Anthony R. West, and there's a material characterization and a Vivian Carter. And these are some online resources. So thank you, sir.